Welcome to Chapter 11, and we're going to be looking at the outer planets today. So without any further ado, let's go ahead and get started. Let me see if I can share my screen here. And let's get to our slideshow. And where is the slideshow? Nope, that's not it. That's the slideshow. There we go. Aha, the giant planets. When we're talking about the outer planets, the giant planets, we're talking about Jupiter, Saturn, Uranus, and Mars. Now, one of the things to keep in mind with all of these planets is that we have had probes go to each of them, so we have very close-up views of each of them. We've only had one ever go out to these two, to Uranus and Neptune. We've had several that have not only gone to Jupiter and Saturn, but have remained in orbit for years at a time. They all have rings, but the only one that has prominent rings is Saturn. It is, of course, Lord of the Rings. We're going to talk about rings and moons specifically in our next lecture, so I'll only touch on those briefly as we're going through today. Sometimes the giant planets, sometimes the gas giants, as they're collectively called, are broken into two subgroups, and we also call these as a subgroup the gas giants, Jupiter and Saturn, and we sometimes call these the ice giants as Uranus and Neptune. That always makes me think of a Game of Thrones kind of character when we do that. But if we're talking about ice giants, you always know we're talking about Uranus and Neptune. If we're talking about gas giants, chances are good we're talking about Jupiter or Saturn, but we could also collectively be talking about all four of them. So just keep that in mind. Relatively speaking, you can sort of see here with the Earth how much larger all these planets are, how much smaller we are by comparison. In terms of mass, how much stuff there is, Jupiter is 300 times roughly the size of the Earth mass-wise. Saturn is about 100 times. That's close as good an astronomy count. When we're talking about the actuality, it's closer to 318 times for Jupiter. But 300 is good enough. Uranus and Neptune are both 15 to 17 times the size of the Earth. When we're talking about volume, how much stuff, how large they are, if Jupiter were a gumball machine and we put in Earth-sized gumballs, it could actually hold more than 1,200, probably closer to 1,320 or so. Earth's inside. So one of the things that tells us is that it's a lot less dense. It's not rocky material, it's gassy material, it's gaseous material. This is a dark realm of the solar system. Jupiter is 5 times as far away from the sun as we are, which means, remembering our inverse square kind of proposition, that means it gets 1/25th of the light of the sun. Saturn is 10 times further away. That means it gets 1/100th of the sun. Uranus is 20 times further away. That means it only gets 1/400th times the size of the sun, the light of the sun. And Neptune is 30 times further away from our planet as the Earth, which means it gets only 1/900th, 30 times 30. The amount of sunlight as we get. So it's very, very dark out there. It's very cold and faint. In fact, some of these planets put off more heat than they get from the sun. As we look at it, here again, we can sort of see as if you were standing at the tops of the clouds. There is no surface on these planets, but if you are at the top of the clouds looking at the sun, notice the sun dims and dims and dims until we get down here to Neptune, and it's very, very tiny. These arc minutes here, remember, a circle is 360 degrees, each degree is 60 minutes, each minute is 60 seconds. So here on Earth, our sun looks big, but it's actually only 1/2 of 1 minute in the sky in terms of size. It gets much, much, much smaller. And this 1 minute, 1 arc minute of size for Neptune means the sun is about the same size as pretty much most other stars in the sky, bright stars in the sky at that time. So it is very, very faint out there. All of this area is outside the frost line. Remember, when you're close to the sun, things will melt. When you're far enough away, things stay frozen. In between, we have our habitable zone, where planets can be not too hot, not too cold. All of these planets are beyond the sun's frost line because it's at 4.5 AUs, 4.5 times the distance of the Earth from the sun. Jupiter is 5 times, Saturn is 10 times, Uranus is 20 times, Neptune is 30 times. So they've all outside of the area been able to keep things that would normally bubble and boil away here around the sun, like hydrogen. So we do have quite a lot of gassy material that has been accumulating out there. Again, here is the giant fact sheet. I would keep this up when you're doing quizzes or questions for this area. The mass, this is how much larger things are in terms of mass relative to the Earth. So again, Jupiter is 318 times the size of the Earth. 300 is close in astronomy. 95 times as large for Saturn. Notice here volume. This is the gumball machine idea that I talked about before. If Jupiter was a hollowed out gumball, then you could put in more than 1,300 Earths. If Saturn were a hollowed out gumball, you could put in 764. Uranus and Neptune you see much smaller, but still, by the time you're at 60 Earths inside, that's pretty big. Notice here, Uranus has lower mass than Neptune, but a larger volume. That's because it doesn't have as much gravity, so the gaseous material spreads out a bit more. Notice this density here. Saturn is really low compared to the rest of them. Saturn is so lacking in density that it would literally float on water. And notice this here as well, number of satellites. This is the number of moons that we know in 2013. This number changes quite a bit. In fact, this number is probably over 100 now. I check NASA on a regular basis to see. A couple of months ago, they announced 20 new moons had been discovered and verified for Saturn. So yes, these numbers change. Rotation period here. Notice this also. Jupiter, even though it's 318 times the size of the sun, the mass of mass of the Earth, it's rotating, it's whipping around in less than 10 hours. Saturn is also whipping around in just over 10 hours. Uranus and Neptune are both going around in less than 1 Earth day too. So that's really, really fast. Inside, they have different structures. Jupiter and Saturn look similar. Uranus and Neptune look similar. They have low mass because they're primarily hydrogen and helium. They've got a few other elements as well. But when we look at them this way, you can see what's happening is you push and push and push, and a gas will turn into a liquid, and a liquid will turn into a solid under pressure. So what we're seeing here is we have at the highest level, visible clouds with gaseous hydrogen. Push that down far enough and it turns into a liquid, push that far down into enough and it turns into what we call here metallic hydrogen. Technically speaking, it doesn't become a solid, but in realistic terms, it's denser than most solids that we have here on Earth. Notice that Jupiter has a lot bigger area of this dense metallic stuff than Saturn. That's because we've got 318 times the size of the Earth over here. We've got only 100 times the size of the Earth over here. So it's more spread out. It's not as dense. Uranus and Neptune don't have enough material to create enough pressure to get to this metallic side here. And all 4 of them have a rocky core somewhere in the center, which if it were exposed would be a kind of a super Earth, a big Earth kind of thing. They all have magnetic fields. Remember, any planet that has a tilt has a season, has seasons. Saturn, Uranus, and Neptune all have seasons. Jupiter is pretty much north and south, straight up and down. It does not have seasons. But we can see that the magnetic fields are a little bit wonky at times, especially with Uranus and Neptune. That's probably an effect of having had some kind of impact at some point in the future, or in the past, I'm sorry. I don't know where my mind is. So yeah, I can predict the future. Ooh, yeah, no, not quite. Because they are spinning around so fast and just whipping around like that, particularly Saturn, which is lacking in density, that means it bulges in the middle. And trust me, I know all about bulging in the middle. And so the gaseous material is being squashed as it bulges out towards its angles of rotation there, and thus we can see how it deviates from being a perfect sphere. We do too, but not nearly as much because we have a lot of solid on our planet and we don't go around nearly as fast. All of the outer planets bulge like this in the middle due to their rapid rotation, but Saturn does it the most because it has the least density. Here's a picture of Jupiter. We've been to Jupiter many, many times. Pioneer 10 and 11, Voyager 1 and 2. The Galileo probe went into orbit for years. The Juno probe is still there. But one of the things about Jupiter is every time we send a probe to the outer planets, we always stop by Jupiter because Jupiter is the gas station. As we are going to another planet, we let the gravity of Jupiter just pull the spacecraft in. As it pulls it in, it's getting faster and faster and faster. Then it will swing around and sort of slingshot it out. And that means we can launch probes with less fuel, with less weight, and less expense. And it can often pick up more speed and get to things faster. Like our New Horizons probe gained at least 2 years in terms of getting there faster by stopping by Jupiter first. So we always take new pictures of it. This is the Cassini probe that was on its way to Saturn. The Galileo probe, which was in orbit for about half a decade, also contained a probe that we could launch into the atmosphere. And this probe then went down and down and down. Now the atmosphere in Jupiter goes down thousands and thousands and thousands of miles. This only actually made it a couple hundred miles before the atmosphere became so dense that the radio signals wouldn't make it through anymore. Plus, as it goes down and down and down into the denser atmosphere, it begins to react to the increased pressure and literally gets crushed. It won't go down and hit any surface because there is no surface, but also at a certain point, the stuff underneath is going to be denser than the stuff over it, and it's just going to hang there. That actually happens in our own oceans here on Earth. If you drop something into the ocean and it is just sort of like something plastic, don't do that, or a tin can, don't do that either. What will happen is there will be a certain layer of the ocean where the water underneath is denser than the thing, so it won't sink any further down. It'll just float there. Unfortunately, we have heard reports from submarines that there are huge areas of trash that stuff gets dumped in the ocean. No, doesn't make it all the way down to the bottom. That's going to happen here on Jupiter as well for any probes that we put in. We can see there's a complex structure on Jupiter of its atmosphere. We have clouds going in different directions. We have some going in this direction, some going in that direction. Just like here on Earth, we have the prevailing winds in the northern hemisphere going in one direction, but above and below it in the Arctic area and the tropic areas, they're going in the other direction. That's what's happening here. And we can see the big red spot. The great red spot that's here is between two bands, and we can see all of these eddies that are flowing off of the turbulence that is around the big red spot. We'll come back to that in a moment. Most of Jupiter is hydrogen and helium. That is similar to the sun. The sun is also hydrogen and helium. So what people have sometimes thought is Jupiter is a seedlet of a star. In fact, if you watch 2001, A Space Odyssey, or 2010, the much, much inferior sequel, just my opinion, at the end of that movie, Jupiter turns into a second star. And so people think, well, if we just had an extra bucket of hydrogen and threw it on Jupiter, it would become a star. It's actually only about 1/10 the size it needs to become another star. So that's not going to be happening anytime soon. We need 9 more Jupiters at least for that to happen. But we do have the building blocks of a star, so we can sort of see what's happening there. As we look down through Jupiter's structure, we can see all the way down to the bottom we have some ice and rock. Now this ice is actually superheated ice, but the reason why it stays icy is it's under huge, huge, huge pressure. That happens here in Saturn as well. Uranus and Neptune, again, they don't reach that metallic phase. They don't have enough material that goes down into it. But as we're looking in Jupiter, we can sort of see the pressure building up as we go closer to the center. We can see the temperature goes up. Remember, K is Kelvin. That's using Celsius, degree sizes, but starting at absolute zero. By the time we're up to 20,000 degrees, it doesn't matter whether you're starting at zero or absolute zero, because you're just hot down there. But this is the interesting thing over here for me, the bars. Remember, 1 bar barometric pressure of atmosphere on us is about 15 pounds per square inch, 14.7 to be closer, but you know, close is good in astronomy. By the time we're getting to this point here, where the gas is turning into liquid, that's called rain, that happens here, the pressure is 500,000 bars. In other words, 500,000 times 15. By the time we get from the liquid to the solid type of material, liquid turning into a solid is snow. We have that here on Earth as well. We're at 2 million bars, so 2 million times 15, that's 30 million pounds per square inch. So our probe that the Galileo dropped in is probably still somewhere in this area here, very near the top. It never even made it to the liquid area. And by the time we get all the way to the bottom, there's so much pressure. We have 100 million bars. That's 100 million times 15. So that's a lot. And that's crushing the core under enormous pressure. There's probably 10 times as much material in the core of Jupiter as there is here on Earth, but it's crushed down into something the size of the Earth. It's like sitting on a suitcase and forcing everything in. So it is pretty dense down there. At the top, however, we have gas clouds that are floating around in the atmosphere, just like we have here on Earth. The upper layer is mostly ammonia. It has a sort of grayish and sometimes a little bluish yellowish tint. We have hydrogen sulfide in the middle here. It has a reddish tint. Remember that because we've got our big red spot, as you can sort of see over here. That's going to be at the hydrogen sulfide layer. And then we have water, good old H2O, and that's going to be at a lower layer here. So they'll sometimes actually cover each other up. Sometimes the big red spot seems to disappear just a bit, but it's actually still there. It's just the ammonia clouds have covered over it. And as it swirls out the ammonia, then in fact, what we see is the red spot still there. Some of these bands of clouds, just like here on Earth, have flows that go down. We have low pressure and high pressure cells. They have low pressure and high pressure cells on Jupiter. And the zones will go in different directions, not only up and down, but also side to side, east and west. These are all heat-driven convection belts and zones, sort of like our temperature changes here on Earth. We have hot air rising, we have cold air that is flowing down. We also have around our planet, we've talked about this before with the aurora borealis, the northern lights, our magnetic field. Jupiter also has that because as it's rotating really quickly and it's got all that metallic material in the center, it turns it into a real power source. It's got a sort of a magnetosphere that includes this thing that's around the middle here called a torus. Notice this torus here, T-O-R-U-S. That's a donut ring of material. Of energy, but it also has material in it because Io is one of the moons of Jupiter that's right in, as it's orbiting, in that torus area. So one of the things that happens is Io has a lot of volcanic activity that spews out material, and that's why I made the blunder and said material, because there is material there. And some of that will then fall into Jupiter, but it also gets charged, charged particles. Here we can sort of see the aurora borealis on Jupiter in great relief. What we see here is this is larger than the Earth. This is probably about 10 times the size of the Earth up here along the way. We have different particles that get trapped in the magnetic field. And right now, the Juno probe is actually trying to do this kind of orbit as well to stay out of that torus of stuff. Here we can see another view of the torus. The other planets don't do this. They don't have a strong enough field to generate. You have to have a really powerful field to get this donut ring of energy along the way. So Jupiter is the only one that does this. Notice here's the Earth's magnetic field times 10 compared to Jupiter. Jupiter's magnetic field is so large, the magnetic field is actually larger than the sun. So it's huge, huge, huge area that's happening here. And remember this Io, this moon Io being in the Taurus. Notice there are other moons out here, they're outside that, but remember this being in the Taurus, because when we get to talking about Io next week, that will be important along the way. Here we can see the other planets in comparison to Jupiter's magnetic field. Here's the size of the sun. So you can see the magnetic field around Jupiter is really large compared to the sun. And we have different magnetic lines as the solar wind is hitting them, even way out at Neptune, even though it's 30 times further away from the sun as we are, and it's only getting 1/900th of the energy, it's still getting hit by particles from the sun. And so we can sort of see that they cause a little disruption for the backside, just as it happens with all of them, but it doesn't cause nearly as much because, again, it's further away. The disruption of Jupiter's magnetic field here with the flow of the particles and stuff will stretch almost all the way to the orbit of Saturn. It stretches all the way 5 AUs away, 5 times 93 million miles. That's a huge, huge amount. So when we're talking about things out in this part of the solar system, we're talking big. Then, of course, we're talking about Saturn. We go from Jupiter to Saturn. Saturn also has hydrogen and helium. Galileo was the first person to see the rings of Saturn, but he didn't really know what they were because, and this is one of the things to keep in mind about scientific discovery. You can see things before you know what they are. You don't often get the credit for discovering something if you just see it but don't know what it is. You have to sort of figure out what it is. He sort of figured out that there's something odd. He thought they were sort of maybe ear flaps or some kind of thing like that. Not technically ears, but you can sort of see from the drawing here. He didn't know they weren't attached. So we give him credit for seeing the rings of Saturn, but we don't say he actually knew what they were. It was another generation later, Christian Huygens, who was a Dutch telescope inventor and refiner, who got a good enough telescope to see that they were actually detached. When we sent the Cassini probe up to Saturn, it had a backpack on it called Huygens, and it actually landed on the moon Titan along the way. We didn't send a Galileo probe to Saturn because we'd already sent one to Jupiter, so we didn't want to confuse things. But the Cassini probe was in orbit for much longer than the Galileo probe. It was in more than a decade. It just sort of went out of commission a couple of years ago. Here we can see a picture from behind Saturn looking towards the Earth. This is a picture of the Earth in 2013. We can see how bright and vibrant the rings are, that even from the back side, because the sun's going to be on the other side, they still are reflecting. They have a very high albedo. Remember that word, albedo? That's the reflectivity that's there. And we've already seen that one. Again, 764 times the size of the Earth in terms of mass, or in terms of volume. This is then the gumball test. If you have Saturn as a gumball machine, this is how many Earth-sized gumballs you could put in. Mostly hydrogen and helium, but it would float on water. It rotates very fast, and that's why it's not a spherical shape in terms of being perfect. It is oblate. That's what we call that oblateness, that sort of bulging in the middle. So I'm not fat, I'm just oblate. It spins around enough that metallic stuff that's inside will actually generate heat. That's happening on Jupiter too, but one of the things is by the time we get out to Saturn, it's putting out more energy than it receives from the sun by about 2.5 times. Jupiter is much closer. It gets 1/25th the light and heat that we get. Saturn only gets 1/100th the light and heat that we get there. So this makes a difference. But again, where that gas turns into liquid, where that liquid turns into a solid kind of thing, we have helium that also goes from gas to liquid on Saturn under pressure. So we have helium rain. That's if you're going, have you ever sucked a balloon dry of helium? Your voice gets all squeaky. You're like a puppet on It's a Small World After All. We could have a ride where you're going through the helium rain. Saturn does have a tilt, so as it goes around the sun, it does have seasons, and we can see seasonal changes in the storm patterns on the clouds as it does its trip around the sun. It has a similar structure in its atmosphere. Again, we have our ammonia and sulfide and water layers, but they're much more spread out on Saturn than they are in Jupiter. Jupiter is much more compact, much more compressed. But it does have some significant storms. Here we see a big storm at the equator. Here we see much smaller storms around the polar region, and we have this interesting hexagon at the North Pole. These are our false color, by the way. These are color enhanced so that we can see the different bands in a better light. But they do show us some interesting structures in the sky. Then when we get out to our gas giants, Uranus and Neptune, they're basically the same structure, but notice they look like different colors. And that's because in large part, they have different seasonal and temperature structures. I'm trying to find something here, and I don't have anything here that is going to be useful, I don't think, well, let's see. So if we're talking about, let's see, if we're talking about, this doesn't want to give me, let's see, okay, so look at this in front of my face. If we're talking about Neptune, remember Jupiter's straight up and down, Saturn's a little bit of a tilt, Neptune's also a little bit of a tilt. Uranus is all the way over here. It's more than 90 degrees. It's on its side. And that accounts for why it looks different here. It looks like a frozen snowball because basically it is a frozen snowball. Uranus is 19, close is good, we'll say 20 AUs from the sun. Neptune is 30 AUs from the sun. We can see that a year on Uranus is 84 years. We can see that a year on Neptune is 165 years. That means each season on Neptune is 41 years. It means each season on Uranus is 21 years. It takes a long, long time for things to change out there along the way. Both have slushy areas of liquid molecular hydrogen. They don't get all the way down into the solid kind of thing. They're each possessing a rocky core at the center along the way. But they're mostly hydrogen and helium, just like Jupiter and Saturn, but they have a higher concentration of methane and ethane, which is what gives them this sort of bluish color. That blue is not water. That blue is, in fact, from the methane and the ethane. So when we compare all four of these, we can sort of see here we have our ammonia, our sulfide, and our H2O clouds, both on Jupiter and Saturn. We've got a couple of other kinds of areas where we've got some haziness that's up here. Then we also have on Uranus and Neptune, we have our methane, ethane kinds of things. Methane and ethane are very close in chemical composition. That's why I keep bouncing between the two of them. Mostly methane, but there's going to be ethane there too. And then we do have some sulfur clouds, but not nearly as much, and we don't get big red spots or anything like that. And then other hydrocarbon ices. Hydrocarbon, that's basically anything with hydrogen and carbon. They can form in different ways. Here we have a picture of, again, on its side, Uranus. It has a ring. We saw the rings, again, just like Galileo. We saw the rings before we knew what they were. We thought they were camera glare. But they are on the side as well, not nearly as structurally prominent or as beautiful in many ways as Saturn's is, but they're there. We do have storms that form on Uranus. We do have a big blue spot on Neptune. Here we can sort of see the really prominent tilt of Uranus. It's more than 90 degrees, 98 degrees to the orbital plane. Neptune is at 28 degrees. Remember, our planet's at 23.5. So that's much closer to us. But you can see the North Pole is pointing here, the South Pole is pointing here as it goes around. So even though it's on a weird tilt, Uranus does have seasons as well. Now, Uranus was discovered by my guy, William Herschel. Talked a little bit about him when I was going to the trip to England along the way. He's the one who discovered Uranus, and I will try to throw up a little bit of a something that shows you what I went to visit in my next lecture here. But he wanted to name the planet George. And that sounds strange to us, except that a lot of things were named for people who were sponsors. Virginia was named for Queen Elizabeth I, the Virgin Queen. Delaware, the state Delaware, was named for a guy named Delaware. Pennsylvania was named for William Penn. The Carolinas, and Georgia, the state of Georgia, named for George. So it's not too weird, except no one outside of England wanted to call a planet George. So it got the name of Uranus, but sort of the reason why he wanted to name it George is King George was paying the bills, and it's the same George that we know here in America, George III. But sort of as a consolation prize, notice the names of these moons around here: Juliet, Puck, Bianca, Cressida, Rosalind, Belinda, Desdemona. If you know your Shakespeare well, then you'll notice Juliet, Romeo and Juliet, Puck from A Midsummer Night's Dream. These are names from English literature. So that doesn't happen on the other moons of other planets. The planets typically are named for Romans, and planets are named for Romans, or moons are named for Romans and Greeks. So this was an early variation. We're now naming them different things as well. But this we can see the moons also go around the way on the tilt. They're going around the equator that's here. So the seasons on Uranus are going to be weird. We have our sort of south pole, where of course it's going to get zero light when it's not facing the sun, much more dramatically than Antarctica would be. The North Pole is going to get zero light over here when it's not facing, again, much more dramatically than our North Pole. And then the equator sort of goes up and down and up and down. It is a weird kind of structure. Now, all of these planets, as they're going around, are generating huge magnetic fields, Jupiter in particular. So Jupiter and all the other planets are kind of radio stations. They're putting out radio waves, but Jupiter in particular puts out huge ones because of that torus that we talked about before. The colorful clouds show us different kinds of structures. Here's the great red spot again, but we have smaller storms that grow and shrink along the way. Here we can see Saturn over the course of several years. Looks very similar all the way through, although notice this is a little bit of a brighter spot in here that fades over time. So we know that storms grow and shrink on Saturn as well. Here's again a false color. We've intensified the colors so that you can see the different bands of clouds. And notice there are lots of smaller structures, lots of smaller things. This is actually the ring, and there's a gap between the ring and the planet. This is from the Cassini probe as well. And then here you can see the hexagon at the top. That's a really weird structure because typically wind doesn't go in those kinds of sharp angles. And even if it did it once, it probably wouldn't do it all the way around. So this is one of the mysteries. If you wanted to do a final project on the hexagon on Saturn, that would actually be a good idea. That would be an interesting idea. Here's Neptune with its great blue spot, its big blue spot here. The blue spot, unlike Jupiter, this red spot that's on Jupiter over here stays in the same spot. It doesn't move north, doesn't move south, it just stays right where it is. Of course, Neptune is tilted, Jupiter is not. Jupiter being straight up and down, the bands of clouds stay where they are. Neptune is tilted, so clouds go up and down seasonally. So this storm actually moves up and down as well. When we're looking at things. And we've been very, very close to Neptune, only once with the Voyager 2 probe, and it got spectacular photos like this. We're sort of seeing the different ice crystals and structures in the upper clouds along the way. We're hoping to go back to Uranus and Neptune sometime, but it's going to be at least 20 years because it's going to take at least 10 years to get out that far. With the probes that we have now, and it'll take another 10 at a minimum for the probes to be planned and funded and built and tested and launched. So it takes quite a while to get out there. That's why we don't send many probes there. We send probes out to Mars every other year. We send probes out to Venus every 2 or 3 years. We send probes out to Jupiter once every decade. And we've only ever sent one to Uranus and Neptune. But here we can see the different things that are happening on Jupiter and Saturn in terms of their complex bands of clouds. Uranus and Neptune, much smaller, have much simpler structures of winds. Here are some storm patterns. We see some smaller storms near the big red spot. We see some sort of swirling eddies. These are turbulent areas. They probably have tornadoes underneath of them. Many of them have hurricane structures. And this great red spot is in fact a hurricane that's been going on at least 300 years. The reason why I say at least is because we haven't had telescopes earlier than that that were good enough to see it. But this could have been there 3,000 years. It could have been there for 3 million years. We simply don't know how long this storm has lasted. But one of the things that we know from Earth is hurricanes tend to come and go in about 10 days. The week to 10 days is about the upper limit. So having a storm here that's lasted for hundreds of years, perhaps thousands or millions of years, is quite dramatic. And of course, these little ovals over here of smaller storms, this is about the size of the Earth. So you can see how much bigger this storm is along the way. We do have a probe at Jupiter right now. It's called the Juno Probe. It is surveying all the different structures of Jupiter. It's trying to get very, very close. First ones we ever sent out. And one of the things to notice about this little section here as we're ending up, notice how much better the pictures get as we go along. Pioneer 10 and 11 are two probes that went out to Jupiter and Saturn in the early 70s. This was quite remarkable considering that we had just landed on the moon for the first time in 1969. So getting all the way out to Jupiter by 1973 was quite something. And notice there are two, Pioneer 10 and 11. When you're building one thing that costs a huge amount of money, you don't want anything to go wrong with it, because if it goes wrong, you've got only the one and it's done. So what you typically do is you build several of them at the same time, because you've set up the manufacturing, you've got all the expertise, you've got all the plans. So you build several of them at the same time. And you launch two of them, because if one of them hits an asteroid, one of them becomes defective, then you've got a backup along the way. And then you've got the extra parts if you need it before things are launched. That's why there was Pioneer 10 and 11, two of them. That's why there was Voyager 1 and 2, there were two of them. Believe it or not, there were two Hubble Space Telescopes. There's the extra one is actually in the Smithsonian right now. But you don't want to just sort of one and done kind of thing. So that's rare. Viking 1 and 2, two things that landed on Mars. Spirit and Opportunity, two things that landed on Mars. We're now getting a little bit better that we will often send just one, but that's risky because if it hits something or becomes defective, then you've lost it. But here, notice here's a picture. Not bad for the 1970s. Voyager went by, and it was the one that discovered Jupiter had rings, and that's when we figured out they all have rings. We discovered it from behind, and we also discovered water on the moon of Europa, and we discovered volcanic activity on Io. Hold those questions for our next lecture next week. Galileo went into orbit for more than half a decade, took lots of great pictures of the moons that were there. It went into orbit around the equator. So it was essentially going around trying to avoid all the supercharged Taurus and other kinds of things, because that can short circuit stuff. So Galileo actually had some problems due to that, but it also did quite a good job for what it had. Cassini, again, as things go to further planets out, they stopped by Jupiter for a gas station fill-up. And notice how much better this picture is in 2000 than this picture was in the 1970s. It's just like me and you, whenever we get a new phone, the camera gets better and better and better. So every time we've sent up another probe to Jupiter, even if it's just passing by, it gets better and better and better. Look at this. This is wonderful, wonderful stuff in the storms, in the Great Red Spot, in the eddies of things like that. Because Jupiter spins around in less than 10 hours, you can actually get a full visualization of it without needing to be there for very long, which is good as well. New Horizons on its way to Pluto, arrived in Pluto in 2015, also stopped by and got this really wonderful picture of Io. Again, we see an eruption, a volcanic eruption happening here. This would cover the United States. That's a huge, huge one that's happening there. And then, of course, we keep tabs on it with the Hubble. The Hubble can also see the auroras that are there. We have to sort of shift the way we look at light to see those, but it's been observing Jupiter for nearly 30 years. This is really good stuff as well. This is better. This is a better picture again than our Pioneer picture. Remember this picture here? Now, even from as far away as Earth, we're getting images like this. So it is quite spectacular. Juno arrived in 2016. It took 5 years to get there and was meant to be in operation for a little under 2 years. And what it does, instead of going around the equator, it sort of goes up and down, and it sort of dive bombs Jupiter. And I'm going to put up a couple of videos from YouTube on the Juno probe so that you'll be able to see it. But this is also the first probe that we've sent out to this outer region. Remember, it's the dark realm. It's come over to the dark side kind of thing, where it's hard to get sunlight. This is the first one we've sent out that has solar power. Notice the size of the guys here. It's got this huge panel. It's got 3 of these. And that's 19,000 solar cells. 19,000 solar cells at Jupiter will generate 500 watts. That's 5 light bulbs, only 5. A typical room in your house will have more than this. And it takes all of this at that range to get that much power. But that's all it needs to be able to operate. So as it was going there, it's looking to try to figure out what's inside of Jupiter. It's looking to find out whether there's water. It wants to explore that magnetosphere more. And that's part of why it goes up and down and skirts away from Jupiter, because it doesn't want to get overcharged. Its original deadline in terms of its mission was to keep operating till February 2018. And it's still going, just like many, many things in NASA. Once they get it right, they get it really, really right. So chances are good it's going to keep going for a long, long time. Galileo, when it finally ran out of energy and had enough damage, it was actually intentionally crashed into Jupiter, so it wouldn't inadvertently crash on any of the other moons that are there. The same thing will happen to the Juno probe once it's all done. And I think that's it for our lecture today. Again, I will post up a couple of videos, particularly on the Juno probe, but I may find a couple of others that talk about some of the outer planet things. So look for that as well. And I will see you at Zoom, or I'll see you next week.